Good afternoon, our students, and welcome to this afternoon's class. Today, we'll be discussing with you a very important topic or concept in statistics. Of course, a very fundamental and foundational distribution in statistics called Bernoulli distribution. Called what? Bernoulli distribution. So, what we have is Bernoulli distribution. Bernoulli distribution. Before we continue our discussion on Bernoulli distribution, I think it is wise that we understand the concept of distribution. What is a distribution in statistics and mathematics? A distribution is a mathematical function that describes all the possible values and probabilities of a random variable within a given range. I explain again. It is a formula. It is a function. It describes all the possible values of a random variable as well as the probabilities of those values within a given range. That's what we call distribution. What we call what? Distribution. Distribution is classified into two major categories, and those two major categories are what we call discrete distribution and what we call continuous distribution. So we have what we call discrete distribution and what we call continuous distribution. When do we say that a distribution is discrete? And when do we say that a distribution is continuous? A distribution is said to be discrete if and only if the mathematical function or formula involved in describing the possible outcomes and probabilities of a random variable is limited to that of discrete outcomes. Discrete outcomes in the sense that these outcomes are countable and equally they are finite. Consider, for instance, a function that assigns a value to the toss of what? Of a coin. When a coin is tossed, you can either get a head or you can get what? A tail, represented with a success and then a failure. These are the possible outcomes of these random variables, and which, of course, that mathematical function will assign probability to them. Therefore, it is a discrete and a finite outcome. Consider equally a mathematical function that is concerned with describing the possible values of a toss of a die. The two possible or the possible outcomes of a toss of a die begins from 1 and ends at what? At 6. Discrete values and equally finite. So a distribution is said to be discrete if and only if that mathematical function describes the possible values and the probabilities of discrete outcomes. Discrete outcomes in the sense that the outcomes are finite and equally they are discrete. That's what we call discrete distribution. There are different types of discrete distribution. Different types of discrete distribution, and these are some of them. Types of discrete distribution. Types of discrete distribution. Permit me to write this in as distribution, please. This is a distribution. Number one, we have the first thing, which of course forms our topic of the day, Bernoulli distribution. So a Bernoulli distribution is a type of a discrete distribution. So we have what we call Bernoulli distribution. Bernoulli distribution. We equally have another important distribution that is, of course, coming from this Bernoulli distribution called binomial distribution. Binomial distribution. We equally have what we call the Poisson distribution. Poisson distribution. We equally have what we call the geometric distribution. Geometric distribution. Geometric distribution. In this geometric distribution, we'll be discussing its first and second kind. So we talk about first and second kind. First and second kinds of geometric distribution. And then we equally have what we call the hypergeometric distribution. Hypergeometric distribution. Hypergeometric distribution. These are some of the types of discrete distributions which we have. And what forms our discussion for the day is the first one called the Bernoulli distribution. So you permit me to clean this. The only thing I would want you to remember for me is that anywhere, any day, in any book where you see these kinds of distribution, they are under discrete distribution because the mathematical function involved in all of them describes all possible values of the random variable, say x or y, where the outcomes of these random variables are discrete and equally finite. So Bernoulli distribution is a discrete distribution, binomial is a discrete, Poisson is a discrete, geometric is a discrete, hypergeometric is a discrete distribution. We'll be taking them one after the other. This one forms our class today. The next class we take up the binomial down the line. So permit me to clean this. So the question is, when do we say that a random variable follows a binomial, a Bernoulli distribution? A random variable, say x, is said to follow a Bernoulli trial or experiment if and only if that random variable x can only take up two possible values. These two possible values are often described as success and failure, where success is represented with 1 and then failure is represented with what? With a 0. And then the probability of a success is given as what? P, and that of the failure is given as a Q. I repeat. A random variable, say x, is said to follow a Bernoulli trial or experiment if and only if this random variable x can only take up two possible what outcomes described as success and failure with their respective probabilities P and Q, where P is the probability of success and then Q is the probability of what? Of failure. And we have a condition. That condition is that probability of success plus probability of failure must give us 1. When a thing like that happens, we see that this random variable x now follow a Bernoulli trial. Consider, for instance, a random variable of either survival or non-survival of a patient in the hospital. There are only two possible outcomes here. It is either the patient survives or the patient did not want to survive. So such a random variable or experiment now is safe to follow a Bernoulli trial because there are only two possible outcomes. A student can either pass an exam or he or she fails the exam. So there are only two possible outcomes here. And because the experiment is limited with two possible outcomes, we say that such experiment follows a Bernoulli trial. You can either graduate timely or you did not graduate timely. These are some of the numerous examples of random variables or experiments that follow Bernoulli trials. And of course, when you graduate timely, the probability of such graduation is what is P. And when you did not want to graduate timely, of course, the probability is what is Q, which is the probability of what? Of failure. So such is what we call a Bernoulli distribution. However, there is also another important definition or explanation of a Bernoulli distribution or trial. We can look at it from this perspective. A random variable, say x, is said to follow a Bernoulli trial or experiment if the mathematical function that is involved in describing the possible values and the probabilities of this random variable x within a given what range can be given as p of capital X equals small x is given as what? P of x q of 1 minus what? X. Such that x can take up only two possible values represented with 0, what? 1. 0 is failure and 1 is what? Is a success. So anywhere, any day, a function, this is what we call that mathematical function. It describes all the possible values of this random variable x, including its what probabilities when it takes up these values. For instance, when this 0 goes in here, we say that this random variable x has taken up what? 0, and that 0 is what? Is failure. We come here. Earlier on, we must have been given the probability of what? Success, which is p, and the probability of what? Of a failure, which is what? Which is q. Now, you now putting what? 0 here and putting 0 here in order to evaluate this thing now gives you now the probability of that random variable taking up a value 0. When 1 comes in here now, you are now trying to evaluate now when this random variable, the probability that this random variable now x now takes up now the value of 1. Now, this thing I have written on the board is what we call the PMF. What we call what? PMF. It is called PMF. This PMF, the full meaning of PMF is what we call probability mass function. Probability mass function. Probability mass function. Mass function. Do you remember earlier that we said that a distribution is a mathematical function that describes all the possible values and the probabilities of a random variable within a given range. That was what we said about a distribution earlier. And this time around, we are talking about what? Bernoulli distribution. And then we have written this now to be that mathematical function, describing the possible values of the random variable, what? X, and equally giving the respective what? Probabilities. Then I now say that this function which I've written here is called the PMF. So if you are talking about discrete distribution, the name that is given to that mathematical function that describes the possible values of a random variable, say x, including its probability, is called probability mass function, otherwise called a PMF. So this thing is called the PMF of a Bernoulli distribution. Anytime, anywhere, the PMF of a random variable, say x or say y or say anything, is given this way, we say that that random variable x follows a Bernoulli distribution with two possible outcomes, 0 and 1, 0 failure and then 1 success. That is what we call Bernoulli distribution. And equally remember that this p plus q here must give us 1. That's what we call Bernoulli distribution. So right now, we want to talk about now what we call the expected value and the variance of a Bernoulli distribution. Expected value and variance of a Bernoulli distribution. Expected value and variance of a Bernoulli distribution. Expected value. Expected value. Another name of expected value of a random variable x is the mean of the random variable x. So you either call it the mean of the random variable x or you call it the expected value of the random variable x. So here could be what could be the mean of the random variable, expected value or mean of random variable. Please permit me to write r.v as random variable x. How is this expected value or the mean of random variable x written and expressed in statistics? The symbol of expected value of a random variable x is given as what? E of x. is described as E of what? Of X. So you are talking about expected value of a random variable X. But when you write E of what? Y, what you are talking is what? Expected value of a random variable, what? Y. So it depends on your definition of that random variable. But ab initio, we already had started making use of X. So let us now restrict our working with a random variable, what? X. So the question becomes now, when this symbol of expected value is written, how is it expressed in statistics? It is expressed as what? This is summation over the range of X. Of what? X. P of capital X is equal to what? X. This is how it is expressed in statistics. Summation over the range of X of this X that is here. Then that mathematical function which we earlier wrote. But remember that we are discussing Bernoulli distribution. So I will now say but. I'll say but. You know that in Bernoulli distribution, the random variable X takes up only two possible outcomes. So we have that X is given as 0, what, 1. And you know that in Bernoulli distribution, our P of capital X, P of capital X being small x, is described as P of X, Q of 1 minus what? X. You remember it earlier. So what I'm going to do is to return back to this expected value. Wherever place I see X, I'm now going to say it runs from 0 to 1. And wherever place I see P of capital X being small x, I will now go with this expression here because they are the same thing. So I will now say therefore, this my E of X. E of X is given as, here is my summation. Here, my X, it begins from 0 and it ends at what? 1. This X is here already, so I have X. P of capital X equals X is already given it. So I have P of X, Q of 1 minus what? X. This is what I have. What am I expected to do here? What I'm expected here to do is simple. I'm expected to evaluate this expression when X is equal to 0 and then when X is equal to what? 1. And I add both of them because that is what sum is doing here. So you and I are going to evaluate this expression when X is 0. We equally evaluate it now when X equals to what? 1. And we sum both of them. When we must have arrived at the sum of them now, that is what we call the expected value of that random variable X. So let us go. So this is equals. When X becomes 0, here is going to be 0. So I have 0 multiplied by. Here is my P. So I have P. Here is X, and X is 0. So raised to power 0 multiplied by. Here is my Q. So I have my Q. Here is my 1 minus. X is taking up 0. So here is going to be what? 0. I am done substituting the value of 0 now anywhere in this expression where X appeared. So I will now say plus. I am going to do the same thing when X becomes what? 1. So I will now come here. In place of this X now, I'll write 1 multiplied by. Here is my P, so I have P. Here is my X, which is 1 raised to power 1 multiplied by. Here is my Q, so I have my Q. Here is my what? 1. X is already 1 minus what? 1. Now, because 0 is multiplying the whole of this quantity, the entire thing here now becomes what? 0. So I'll quickly write what? 0 plus. Of course, you know that here is 1, so I have 1 multiplied by. In mathematics, anything raised to power 1 is itself. So this P raised to power 1 is what? Is P multiplied by. Here is 1 minus 1, and 1 minus 1 will give me what? 0. And anything raised to power 0 in mathematics is what? Is 1. So here is equally what? Here is my P, here is what? 1. Now, of course, you know that 1 times P times 1 will equally give us what? P. So this thing becomes what? 0 plus what? P. And when 0 is added to anything, it doesn't change it now. So here becomes what? Our P. So the expected value of a Bernoulli distribution or a Bernoulli random variable is given as what? P, being the probability of what? Of a success. So anywhere, anytime you are asked that kind of question, bear it in mind. If somebody says that the probability of a success in a Bernoulli trial is 0.75, What is this is expected value? Is expected value is equally 0.75 because is expected value is the same thing as the probability of success. Note that. Somebody can equally tell you because of this thing now, say if the probability of success in a Bernoulli trial is, if the probability of failure in a Bernoulli trial is 0.25, what is the expected value? You remember that I earlier told you that probability of success P plus probability of failure is given as what? As 1. And somebody has given you that the probability of failure is 0.25. So what you are going to do is that P plus 0.25 is equals to what? 1. This and this are like terms. P is equals to 1 minus 0.25. Then this 1 minus this will now give you what is called 0.75. Okay? So when they give you the probability of what? Of success, they can ask you to find the expected value. And remember that the probability of success and expected value are the same thing. They can equally give you the probability of failure, the one they gave you here, and require you to find the probability of success and as well as the expected value. It's just for you to make your P the sort of formula, and whatever thing the P becomes now is both the probability of success and as well as the expected value of the random variable X. Thanks much for your audience. This is how to go about now for you to obtain the expected value of a random variable X that follows a Bernoulli distribution. So I'm going to clean this board, and with you, calmly, we look at the variance of the variance of a random variable X that follows a Bernoulli distribution or trial. Okay, we're now talking about variance of a random variable X. Permit me to write R dot Q, a random variable X. And this random variable X now follows a Bernoulli distribution. First of all, we are going to write the formula of a variance of a random variable and then transform it now into that of a Bernoulli distribution. The formula for a variance of a random variable X is given as what? We have V of what? Of X is given as, we have what? E of X raised to power 2 minus E of X, then all in brackets raised to power 2. This is the formula with which to evaluate the variance of any random variable X. So what we are going to do now is we are going to start from this one. We now say but. Our E of X raised to power 2 should be given as, we have summation over the range of X of X raised to power 2. P of capital X is equal to small x. Remember that when I had something like this, E of X, I say it is summation over the range of X, P of capital X equals X. So I took only this X that here and put it here. Here we are talking about X raised to power 2. So here now, what I'm going to have here is X raised to power 2. Now, but we are not talking about Bernoulli distribution. When we are talking about Bernoulli distribution, we now say and. Here our X takes a value 0, 1. And we know that P of capital X being small x is expressed as this equals P raised to power what? X. Q raised to power 1 minus what? X. You remember this. This is how it is expressed. So what I'm going to do now is to return back here. Include the range now, remove this in now and replace with this before I solve on. So I will now say therefore, E of X raised to power 2 now is given as, we have summation. X now is running from 0 to 1 of X raised to power what? 2. Instead of writing this, I will now write this. So I have P raised to power X, Q raised to power 1 minus what? X. What am I expected to do here? What I'm expected to do here is simple, like I earlier had said. To evaluate this quantity or this expression when X is 0 and when X is what? Is 1. And the moment I'm done with evaluating it, I now revert back to this formula, put it here and subtract whatever, and by that, By that, we must have arrived at the variance of the random variable x that follows Bernoulli distribution. So do it with me. D is equal. When x takes 0, here becomes what? 0 raised to power 2 multiplied by. Here is my p. I have p. Here is p raised to power 0 multiplied by. Here is q. So I have q raised to power 1 minus 0. So I have plus. X is now taking 1. So you put 1 here. 1 raised to power 2 multiplied by. P raised to power 1 multiplied by. Q raised to power 1 minus what? 1. And like I earlier had said, there is a 0 here. So when that 0 multiplies everything here, it goes. So plus. 1 raised to power what? 2 is still 1. So here is still 1 multiplied by. P raised to power 1 is still what? P multiplied by. 1 minus 1 is what? 0. Anything raised to power 0 is what? Is 1. 1 times P times 1 is what? P. Added to 0 is equals what? P. So my E of x is equals to what? E of x raised to power 2 is what? Is P. I will now come here and say, therefore, here is my var of x. Var of x is given as. This quantity has been evaluated to be P, so in place of it, I will write what? P minus. I want us to look at what is inside this bracket. What is inside this bracket is E of x. And we called E of x now the expected value of a random variable x. And we earlier had evaluated it, and it gave us what? P. So what is inside this bracket is what? Is P, which of course I'm going to square. So it becomes what? P all raised to power what? 2. So this is going to give me, here is what? P minus P raised to power what? 2. Of course, I can factor something here. There is P here and there is P here. So I can take 1P. So this is P into 1 minus what? P. And remember that if you have something like this, if you have that P plus 1 plus Q is equals what? 1. If you make this P subject to formula, or you make this Q subject to formula, you are going to see what? Q is equals, here is what? 1. This P will come over here, minus what? P. So 1 minus P is the same thing as Q. And what I have here is what? 1 minus what? P. So I can easily remove this 1 minus P and replace with what? Q. So by implication, this thing is the same thing as what? P, Q. And this is a variance of a random variable x that follows a Bernoulli distribution. Okay? Thank you for your audience so far. So the moment you are asked to find the variance of a Bernoulli distribution, you will first of all obtain its expected value. And the moment you are done, you now come and evaluate that of e raised to power 2, e of x raised to power 2. And then you now come and solve this thing here. Thank you for your audience so far. Permit me to clean here while we talk about what we call the moment generating function of a random variable x that follows a Bernoulli distribution. Okay? So we are now talking about moment generating function. Moment generating function. Moment. Generating function is always written as MGF. MGF. Moment generating function. So the first thing we are going to do is to write the formula for the moment generating function of any random variable x. Whether it's following geometric or whether it's following anything, we first of all write it. At the end of which we tailor it down now to Bernoulli, which is the distribution we are discussing today. Now the MGF, the moment generating function of a random variable x, is given as this way. It's given as m. But first of all, what is moment generating function? This moment generating function is a function that enables us to alternatively look at the probability distribution of a random variable x without necessarily looking at or working directly with the PMF, PDF, or what the CDF. An alternative way of looking at the probability distribution of a random variable without necessarily looking for either the PMF or the PDF or the CDF of that random variable x. And like the name implies, it's a moment generating function. So we can actually use this MGF now to generate the moment of a random variable. We can equally use to generate the moment of a random variable. And because we can use it to generate the moment of random variable, we equally need to even understand what we call moments. First moment about 0 is what we call the expected value. First moment about 0 is what we call the expected value. Second moment about 0 is what we call the variance. So at the end, we can decide to use this MGF now to generate the first moment and the second moment, which is equally going to give us that our P and that our PQ that we had earlier solving direct from what? The PMF. So let me first of all now write the formula for moment generating function. The formula for MGF is given as what? That M of x of t is given as what? E of t of x. This is how to write it. Now, and remember earlier that when we wrote something like this, E of x, we say it is expressed as summation over the range of x. This x that is here, x. P of capital X equals small x. This capital X is a random variable. This small x is the realization or the value of this random variable x. So when you have this, you can be expressed like this. So let me now use the idea of this now and express this. By implication, I will now say therefore, this my MGF, which is E of t raised to power x, is going to be expressed as summation over the range of x. What is inside here is what? E of tx. P of capital X equals small x. This is how it is going to be expressed. But we are discussing the Bernoulli distribution. So we need to remember that for Bernoulli distribution, P of x equals capital X, how it is expressed. And then the possible value of this x for Bernoulli distribution, which of course is that our x takes a value of 0,1. And P of capital X being small x is given as what? P raised to power x, Q raised to power 1 minus what? X. You remember that. So what I'm going to do is to return back here. And then if I return back here, I'll be able to say that this equals, I have summation. Here is now my s is running from 0 to what? To 1. Here is now E of t raised to power what? X. I won't write this one again, I will write the other one, which is P of what? Of x. Q of 1 minus what? Of x. Like I've always said, what is it that is expected of me here? What is expected of me here is to evaluate this expression when x is equals to what? 0. And evaluate it when x is equals to what? 1. Sum both of them now, and by then, I must have arrived at the moment generating function, MGF. So I'll now come here, I'll say that this equals, here is my E of t. Here is x and it's going to be 0. So I'll open a bracket and put 0, multiply by. Here is my P, here is x of what? 0, multiply by. Here is my what? Q, here is what? 1 minus what? 0. I am done putting that of 0, so I come for 1 plus. Here is my E of what? T. This my x now is 1, close it, multiply by. Here is my P raised to power 1, multiply by. Here is my Q raised to power 1 minus what? 1. T times what? 0 is 0. And E raised to power 0 is what? 1. Because anything raised to power 0 is what? Is 1. Multiply by. P raised to power 0 is 1. Because anything raised to power 0 is what? Is 1. So this is 1 times Q raised to power what? 1. Because this 1 minus 0 is just like Q raised to power 1. And Q raised to power 1 is just like what? Q. So the whole thing I have here is what we call what? Q. Here is Q. The sign here is what? Is plus. Then I come over here. When I come over here now, it is equally simple. Here is my t times 1 is what? Is t. So what I'm going to have is what? E of what? T. Because this t times 1 will just give me what? T. Multiply by. Here is my what? P. Multiply by. Here is my 1 because 1 minus 1 give me 0. Anything raised to power 0 is what? Is 1. So this will give me that this becomes what? Q plus P of E t. This formula is what we call the moment generating function of a Bernoulli distribution. However, when you are going through the pages of what of a textbook, oftentimes you see a little variation of this last expression, but then it doesn't change anything. Do remember that I had earlier told you that P plus Q is equals 1. And on that note, our Q is equals 1 minus what? P. So you can decide to come here in place of this your Q, you use 1 minus P. So at times you see them write in the textbook something like this, where they say 1 minus what? P. In place of this Q, which is what is here, then they will say plus P of E of T. This is equally a formula for that. So you either report this or you report this. Thank you very much for your audience so far. Permit me to clean here. So when they ask you about the moment generating function, this is what we do. So what we are going to do now is to see whether we can come and hold the MGF, and from the MGF now generate the moment. That's what we are going to do. So it permits me to clean the board. Let us do that one. So we have generation of moment from the MGF. Generation of what? Of moment from the MGF. Generation of moment. Of moments from MGF. How do we generate moments from the MGF? What we do is, if we are talking about the first moment, we differentiate the MGF once and evaluate what we have when t is equal to 0. If we are talking about the second moment, which is of course the variance, we differentiate this MGF what? Twice and evaluate when t is equal to what? 0. So that's what we are going to do. And then when you are talking about rth moment, you are going to differentiate this MGF now r times, and then you evaluate when t is equal to 0. So oftentimes when you go to textbook, you begin to see something like this. They will now tell you E of x raised to power r. This is rth moment about 0. About what? 0. They will say this equals capital what? M of x of t. They will now write what? R. R, they are writing here that you must have differentiated this in up to what? R times. That's what they mean by that. Permit me to remove what came up on my camera. So this is what they mean by that. Now this thing is the same thing as someone saying d dt of m g f. Differentiating the MGF with respect to what? T. R times. But this time around, we are talking about for now first moment. So anywhere I see R, it becomes 1, 1. We are talking about the first moment. So we now have what we call E of x raised to power 1, which is equal to M of x of t raised to power 1, which is what? D of 1, d what? T. Remember that MGF of a Bernoulli distribution is given as Q plus P of E t. Remember this. And remember anything raised to power 1 is 1. So this is just like I am differentiating this thing this way once. So what am I going to do? Let me first of all open this bracket with this differentiation symbol. So this thing will now be able to give me d dt of this one Q plus. Coming here, I have b of what? dt of what? P of E t. And I'm differentiating this Q with respect to t. But there is no t contained here. Therefore, it automatically becomes 0. So the whole of this thing here becomes what? 0. I have 0 plus. I'm differentiating this with respect to what? T. And look at where this t is contained. So it's just like I'm differentiating e raised to power 2. And the derivative of e raised to the power 2 is just e raised to the power 2. So the same, so I'll just write what I have here. I have p of e raised to the power what t. Because the derivative of e raised to the power 2 is e raised to the power 2. And then this might be the coefficient which is supposed to be there. And I'm told that I have to evaluate what, okay, 0 plus this thing will equally give me p of e raised to the power what t. So the first derivative of this MGF is p e of t. So I'm going to evaluate this thing now when t is equal to 0. So I will now do something here and say t is equal to what? 0. When t is equal to 0, what I'm going to have is what? P, here is my what? E, here becomes what? My what? My 0. Anything raised to power 0 is 1. So I have 1 times p, and this becomes what? P. So the first derivative of the MGF of a Bernoulli distribution already has given us the expected value e of x, because anything raised to power 1 is just like e of what? Of x. That's why we use the word moment generating functions. So we can actually use the MGF now and generate the moment of a random variable from is PMF or PDF. Okay? So permit me to clean here while we now talk about the second moment. Talk about what? The second moment. Okay? So you permit me to clean. Okay, we are now talking about the second moment. So permit me to put 2 here, permit me to put 2 here, and permit me to put 2 here. So I am meant to differentiate this thing twice. And you know that when I differentiated once earlier, the answer I got is P of E of T. That was the answer I got earlier. So differentiating this thing twice is as good as differentiating this thing once. So by implication, what I have here becomes what? D dt of P of E raised to power what? T. Once I differentiate this thing twice and differentiate this thing once, the answer I'm going to get are the same thing. And when you come here, when you are differentiating this now what? Once. Remember that derivative of e raised to power 2 is still e raised to power 2. So which means what you have here now, the derivative of this now is not going to give you what? P of e of what? Of t. When I want to evaluate this thing here, I'll just put that t is equal to what? 0. Here becomes p of e raised to power 0. And then this will be able to give you what? P. What can we say about this? The first moment gave us P, and the second moment gave us what? P. It is from this first moment and second moment that we can find the variance of a random variable. And remember that we told ourselves earlier that the variance of a random variable is given as what? var of x is given as what? E of x raised to power 2 minus e of x all raised to power what? 2. This is equals. I have gotten that e of x raised to power 2 is p. So I have my p minus e of x inside this bracket gave us p earlier with this square here. So I have p raised to power what? 2. Like I said earlier, this equals p into 1 minus what? P. And 1 minus p is q. So this equals what? P, q. So and we have gotten the variance of that random variable, what? X, that follows a Bernoulli distribution from the MGF of that random variable x. So this is actually how to generate all those things from them. Thank you very much for your audience so far. Permit me to clean, and when we clean, let us discuss what we call the characteristics function of a random variable x, the characteristics function. So permit me to clean. So we are talking about the characteristics function. Talking about the characteristics function. Characteristic function is always written as CF. It's always written as CF. The characteristics function, of course, has properties or qualities that are close to the MGF, but it is more valuable than MGF. Number one, the characteristics function completely, the word completely characterizes the distribution of a real valued random variable. It characterizes what completely. So since the C dot F or the characteristic function is like knowing or seeing everything about the random variable x. Number one, we can use this characteristic function now to generate the what? The moment, which is the same thing as what the MGF what does. Number one. Number two, uniquely, a function that is even the MGF doesn't do, you can use the characteristic function to obtain the associated distribution of a random variable, which MGF cannot do. That is, you can from this come to know that mathematical function that describes the values of what a random variable and its associated probabilities within a given range. You can do that. Yes. And then again, we can use this word characteristic function to prove that two distributions are equal. So these are functions that we use this characteristic function now to achieve. So the question is, how do we write the characteristic function? How do we express it? How to write the characteristic function is here. Characteristic function is written as what? Our C dot what F is given as what we call E of T x I. This is how it is given. E of T of x what I. Or you can equally write it this way. You can say E of T of I x. So by introduction of this I here now, of course, we now come to know that this characteristic function is a complex function. It's a complex function. So we should note that it's a complex function. So, and of course, we have taught how to express this. So this expression is going to be that E of T of Ix is going to be given as summation over the range of x of E of T of Ix of P of capital X equals to small x. And we know x is equals to 0,1 for Bernoulli. And then we have that P of capital X equals to what? X is given as what? P raised to power x. Q raised to power 1 minus what? X. We should not always forget that. So what I'm now going to do is to come and put them here. So this equals summation. X is running from 0 to what? To 1 of E of T of I what? X. Then we now have what we call of P raised to power what? X. Q raised to power what? 1 minus what? X. We have something like this. Like I've always said, we have to evaluate this when x is equal to 0 and evaluate it when x is equal to what? 1. And by doing so, what we are going to have becomes that is equals, here is my E. So I have my E of T of I to 0, multiplied by here becomes P of what? Of 0. Dot. Here is my Q of 1 minus what? 0 plus. I now come when it is 1. I have E of T of I of 1 multiplied by P of 1 multiplied by what? Q of 1 minus 1. So this becomes, because of this 0, when you multiply Ti, everything becomes 0. Anything raised to power 0 is 1. So this is just like 1 times Q. Because Q raised to power 1 minus 0 is just like Q. So I have my Q there. Plus. So when we come here, this I multiplying this 1 will just give me I. So I have my what? My E, T, I multiplied by. Here is my P, so multiply by P. 1 minus 1 will give me 0, and anything raised to power 1 is what? Is 1. Anything raised to power 0 is what? 1. Multiply by this will give me the same thing. So this is the same thing like writing that this is Q plus P of E of T of I. Which as well you can see as 1 minus P plus P of E of T of I, based on the explanation that I had earlier given. So this is how to obtain the characteristic function of a Bernoulli distribution. Stay tuned, because from henceforth we will be picking all the distributions and discussing them one by one. However, when the size of the class becomes large now, we can cut the class and then speed it now to the next class. Because when we go over to binomial and Poisson, most of the things we are going to do now begin to expand. Thank you very much for your audience so far. Do not forget to subscribe to our YouTube channels. Don't forget to share and like our videos. Thank you very much.